So now that we have an idea about our p-value of 0.119, let's sort of wrap up what we can say about a research question and think about this a little bit more. Oops. Go back here. Sorry. Okay. So when this was done before, p-value of 0.11 was reached, that's an old value. You could do this many different times and we get slightly different p-values, but, it's pretty close. 0.12 basically here, 0.11, so it's about the same. So again, we have this idea that obtaining, clicking on the wrong thing. We have this idea that obtaining a sample proportion of 0.64 or something more extreme than that is fairly likely. It's about happened about 12% of the time in our simulation, assuming that the true proportion is 0.5. So given that that's fairly likely, that says something. And the cutoff for statistical significance that we tend to use in statistics is 0.05. We call this our alpha level. Our alpha level is the probability level that determines statistical significance. It's the level of likelihood of obtaining a sample result or something more extreme, assuming a null hypothesis is true, at which we say statistical significance is occurring, that is unlikely to just be random chance. So we set a likelihood level of about 0.05, about 5%. We say 5% sounds unlikely. Anything less than 5% is unlikely to occur just by random chance. So since our p-value is about 11% or 12%, that's higher than our alpha level. And we say, well, 12%, that's reasonably likely to happen by chance. Therefore, this original sample result of 16 out of 25, giving us a proportion of 0.64, that's pretty likely to happen by chance, assuming the null is true. If we're assuming the null is true and this likely occurs, then we can't reject the null. And basically, that's where it ends. We do not have evidence to reject the null hypothesis, and therefore we do not have evidence that people can match dogs to their owners beyond random chance. Now, we don't have proof that it's just random. We don't have proof that the true population proportion is 0.05, is 0.5. That's a different logical debate to get into, which we'll save for another time. We simply say we cannot reject our null model, our null hypothesis of 0.5. And so that's it. That's where it ends. We don't have evidence that dogs can guess better than random chance. So that's the end of our research question. That's all there is to it. So let's play with a hypothetical, though. What if, instead of getting 16 out of 25, as we did in our original sample, what if we actually got 18 out of 25? What if in our sample the proportion was 0.72, or 72%? How likely is it to get 72% or 0.72 as a proportion, assuming that just random fluctuations, just random chance is at play in our world? Well, we already have the randomization distribution under the null hypothesis that we care about. So let's just plug in our hypothetical value of 0.72. Okay. So if our original sample were actually 18 out of 25, we obtain that proportion of 0.72 or something more extreme than that 2% of the time. That's a lot different than the 12% from before. So in this case, we get a p-value equal to 0.02. And since 0.02 or 2% is pretty unlikely and is less than our statistical significance likelihood threshold level, whatever you want to call it, of 0.05, we can reject this null hypothesis. Again, if we get a sample proportion of 0.72, and this is the world that we're working under, that we're assuming is true, then this is not a good world for this sample data. This sample data, 18 out of 25, does not fit well in this world of the proportion being 0.5. Therefore, we reject this notion that it's 0.5. That's what rejecting the null hypothesis means. We say, assuming a world where the population proportion of matching dogs to owners is 0.5, if it does not produce our sample data with much likelihood, then it's not a good world. Then it's not a good assumption, and we can reject this null hypothesis. And that would lead us to say that gives us evidence in favor of the alternative hypothesis, that there's evidence that dogs can be matched to their owners beyond just random guessing, beyond random fluctuations, that proportion in the population of guessing is greater than 0.5, greater than 50%. So again, if it's 18 out of 25, that reduces our p-value, that reduces the likelihood of obtaining this observed result or more extreme, assuming the null is true, to 2%, 0.02. And we reject the null hypothesis and say, yeah, we've got evidence that dogs can be matched to their owners. So that's this example of a single proportion. Now in the discussion activity, we're going to go on this idea that's brought up in the book that there's a 19th century claim that the normal human body temperature is 98.6 degrees. Well, we suspect that maybe it's not that. We suspect that maybe it's not 98.6 degrees. So our research question asks, is the average body temperature for healthy humans actually 98.6 degrees? Well, let's follow our convention of the hypotheses. If we suspect that it's not 98.6 degrees, then our alternative hypothesis is that the mean population body temperature is not 98.6 degrees. And therefore, the null hypothesis, the uninteresting result, the status quo result, is that the mean population body temperature is 98.6 degrees. And what you will do in StatKey, is do a randomization distribution just like we did here for matching dogs. We're still going to assume the null hypothesis is true. And what that means is that we're going to assume that in our world, the true mean body temperature is 98.6 degrees. And therefore, when we do our bootstrapping from our body temperature data and remake this nice distribution of bootstrapped mean temperatures to make them look like they are in the world of the null hypothesis, we simply shift that bootstrap distribution over to the center of 98.6 degrees. So again, you're just going to be bootstrapping and sampling with replacement just like before from the original sample, except we're going to shift every single one of those means such that the center of the whole thing is at 98.6 degrees. And that will look like the world under the null hypothesis, which is our objective when we do the randomization test. And after you do that, you will follow exactly like we just did before. We will find the p-value, and we will say, given that p-value, is it likely or unlikely to get a sample average as or more extreme than 98 0.26 because that's our true sample value. And then we'll ask the same thing, based on that p-value, do we reject or fail to reject the null hypothesis, and what does that say about our research question? Now, one other quick thing about this. So in our matching dogs example, the alternative hypothesis was what we call one tail, because we guessed a direction greater than 0.5. And so we did what was called a one-tailed hypothesis test, because we only looked at the p-value given one tail, the right tail. That's what our guess was about. Well, now the situation is a little bit different with the body temperatures, because, because now our alternative hypothesis is that we're not guessing greater or lower than 98.6. We're just saying different than 98.6 degrees. Therefore, to show you, when you do your p-value, you're not going to click left or right, you're going to click two-tail. When you do a two-tailed hypothesis, you click two-tail, and then, for example, if the proportion, if I had done a two-tailed hypothesis for the matching dogs example, I can just put in a proportion, like before, 0.64, and it will symmetrically go to the other tail, because if I had done a two-tailed hypothesis, I would not be guessing a higher than 50% or lower than 50% proportion. I would say, maybe the proportion in the population is much greater than 50% or much smaller than 50%. So I need to look for symmetrical results in both tails, and I would get a p-value that's basically 2 times 0.119, or 0.119 plus 0.119, and I would get a p-value of like about just under 24%, about 0.2398. Excuse me, about 0.2398, something like that. So what I'm saying is, when you do this body temperatures example, since we're saying that the mean, our alternative hypothesis is that the mean population body temperature is not 98.6. We have to check symmetrically our observed result in one direction and whatever the same distance is away in the other direction, and add up those two tails for our total p-value. And I can explain more of that as we get there to the activities. So that's what that will be. And just some quick last notes about p-values. Again, we reject our null hypothesis when the p-value is less than 0.05. That can be fuzzy depending on the field you're in, the context, but for this class, we can just say if your p-value is less than 0.05, we reject the null hypothesis. We tend to always report it as a proportion, so don't write it as a percent, just write it as a decimal. And we never obtain, so you may obtain a p-value of 0 in StatKey, where just none of the simulated means or proportions are where your sample mean or proportion is. It may be 0 in the simulation, but in reality, it never actually is 0, because we always say that there's just some tiny chance even of getting the observed result just by chance. So we just say that the p-value is either close to 0 or less than 0.001 if it ever is 0 in StatKey. So, for example, if my true proportion was, if I got every single one of them correct, 100% here. Let's do right hand. Every single one was correct. And I got a proportion of 1. That never showed up in the simulation. And it gives me a p-value of 0. Is it possible we get 25 out of 25 correct? Exactly. Yes, it is. It's really unlikely. So we never say a p-value of 0. We just say a small p-value less than 0.01, close to 0, etc. Okay, and on to the next video.